So question 2 on the motor. When Hugo presses a button on the car's remote control, a switch closes to allow current to flow in the coil of the motor. So we can see that just there. This causes the coil to rotate, which makes the car's wheels turn. So that's just how the motor works. The motor has a very simple design. The current in the coil causes it to rotate in the magnetic field. So we've got current coming in here, and we've got the coil, and we've got north-south, and there's interaction between the magnetic field induced in the coil and the permanent magnetic field from the magnet. Between the two magnets shown on the diagram, as the coil rotates, a back EMF is produced in the coil. That's interesting. A is explain, let's just cruise down a little bit, explain how this back EMF will increase the life of the battery. In your answer, you should explain why EMF will be induced in the coil as it turns, explain how this EMF will change as the coil rotates faster, explain the effect of the EMF on the current drawn from the battery. Okay, so I might just jot down brief notes as we do this, but it's kind of leading you through it really nicely. The big picture thing is, remember, whenever you have a coil and you have a changing magnetic flux in that coil, you induce a voltage in the coil, and that voltage is going to charge the battery. So the details though, first of all, let's just go through it. Explain why an EMF will be induced in the coil as it turns. The key idea here is that as it turns, okay, the turning leads to a change in magnetic flux in the coil. Okay, the permanent magnet's there, the coil is going in and out of the flux, and because the tricky bit here is you're running current through the coil to produce a magnetic field, and that magnetic field interacts with the permanent magnetic field, but there's also just the idea of it turning from the motor and coming in and out of the permanent magnetic field. So you can actually forget about the whole motor part and just consider the turning of the coil in and out of the magnetic field that's pre-existing. So the turning causes a change in flux. The change in flux leads to an induced voltage from Faraday's law. And yeah, that's pretty much it. Explain how the EMF will change as the coil rotates faster. So the induced voltage is proportional to, well, let's just write Faraday's law, it's right, equals negative L change in current over change in time. So that change in time is this is actually a different form. Sometimes you'll see it as with this top bit being change in flux. Or negative change in flux. But anyway, the key part here is the change in time. So the faster the coil rotates, the shorter that time period between which it takes to turn in and out of the magnetic field. So a larger change in time smaller change in time from a faster spinning coil leads to a larger induced voltage. Explain the effect of this EMF on the current drawn from the battery. So that's going to be, according to Lenz's law, in the opposite direction to the force which has produced it. So that's going to lead to a longer lasting battery, which is exactly what the question is going to getting to. It's limiting the amount of current in the coil from the battery, and therefore the battery will last longer. That's the whole question. Okay, I haven't written it all down, but hopefully you've got it from the commentary. Hugo decides to use a capacitor instead of a battery to power his remote-controlled car. He knows, and that's a good idea with supercapacitors these days, but he knows the capacitors have no internal resistance and can be recharged. Hugo uses a 500 farad capacitor. That's huge, 500 farads, just so you know. In place of the battery, the capacitor is charged to 4.5 volts and then connected to the car's motor as shown. A deceptively simple circuit. A voltmeter is placed in the circuit. The following graph of voltage versus time is produced as the motor runs. Ooh, I hate these big long questions with lots of lead up, but they're really good because you have to understand the context really carefully and make sure you read it very carefully. Okay, prediction. Whenever you see a graph and you're dealing with capacitors, there's going to be something to do with the time constant, which remember is a drop of 63%. So we'll get to that. B, show that the effective resistance of the car's motor is approximately 4.8 ohms. Okay, how are we going to do that? We're probably going to use the time constant from the graph, knowing that the time constant equals, let's write this down, so the time, I'm going to write it on the graph, time constant equals RC. The time constant is about 63% of the drop, so if we go from 4.5 down to, 63% of 4.5, if it was 5 it would be about 3 volts drop, a little bit less than that, so it's going to be a little bit less than 3 volts drop, which will take it down to about 1.5, 1.6. So where's 1.5, 1.6? Around about here. So that's probably going to be about the time constant, is about 2,500. Okay, give or take. If you do this really precisely and actually calculate the values, you might get 2,400, 2,600. I'm estimating here for the sake of covering the principles more than anything. So we know 2,500 seconds equals the resistance, R, which is unknown, which is what we're trying to find out, the effective resistance there, times the capacitance, which is 500. That's really nice. That gives us an easy calculation. So 2,500 divided by 500 equals R, which means R is about 500 ohms. Is that right? What have I missed here? No, it's not. It's about 5 ohms, because the zeros, 2 zeros will cancel. 25 over 5 is about 5. Okay, so about 5 ohms. And just double check on the marking schedule, it says 4.8 ohms, so, and they use 2,400 for the time constant, so they calculated it just a little bit more precisely. Okay, C, calculate the size of the capacitance required to triple the time constant and draw a new curve on the graph opposite showing this. So two things, so calculate the capacitance required and regraph. So the capacitance required, again we're dealing with T equals RC. To triple, we just have to times the capacitance by 3. So it's going to be 500 times 3 is 1500 farads, capital F. And if we're going to draw this on the graph above, I'll just draw it in red so that you can see a little bit better. That's going to make 3 times the time constant. So it's going to reach this level here 3 times slower. So 2, 500, 500, and then another 7, 500. So there it goes right there. And it's going to have a nice curve down there. My phone's ringing, so I'll just pause. Okay, sorry for the interruption. It's my wife. She's pregnant and overdue for the birth of our baby. I thought it might have been an emergency call. You get interesting things on this website, don't you? Carrying on anyway, so we saw that the curve is going to be stretched out. The time constant is 3 times longer to get to that point. I think we're moving on to the final question now. D, describe using words or by sketching a circuit diagram how this new capacitance could be achieved with 500 farad capacitors. Okay, remember, I'm going to go back a little bit. Resistance formula, this is for resistors in parallel. That's the same as for capacitor, that's parallel. That's the same as for capacitors in series. And that reduces the resistance or the capacitance, depending on what you're dealing with. So we're after the other one. We want to add the 500 capacitors to get 3 of them. So we're after C1 plus C2 plus C3, which is the same as resistors in that's in parallel, which is the same as resistors in series. Okay, long story short, this is how we add them, but they're in parallel. So we're going to draw a picture like this. 1, 2, 3, really badly drawn, but you get the picture, you get the idea. They're added in parallel in the physical sense, but you add them in this way. So that's how they're each 500 farads, which again is still ginormous. They will definitely be supercapacitors, which is quite recent materials technology has allowed us to get there. Anyway, that's the end of question 2.